Okay, we're going to continue looking at different types of integrals, and essentially we have a bunch of tricks to do our integration now. So we want to look at integrals that we can't solve yet and say, what trick do I need to learn so I can do that? So as an example, suppose I want to integrate 1 over x squared minus 1 dx. And looking at it, U substitution is out, it's not a polynomial, it's not trigonometric. I don't have a square root, so even trying to pull a trigonometric substitution seems like it might be iffy. And all things being equal, I mean, that's an incredibly easy looking integral, and yet still it seems like we can't come up with a trick to solve it. In order to do it, we need an algebraic trick, and I don't want to spend an incredible amount of time on this trick. We'll go through several examples, but what I mean is it's an algebraic trick that you actually see in pre-calc, and I should have some videos that I use for my pre-calc students going through this, and I'll upload those along with the videos for this integration, so that if you didn't go through it in pre-calc, or if you did but you only kind of vaguely remember it, that will give you more practice on the algebraic trick. We're going to do it here, but if you think you need more practice with it, I'll upload those videos too. And the idea is we want to use what's called partial fraction decomposition. And essentially, before I do that integral, I'm going to algebraically manipulate the fraction using partial fraction decomposition. And again, if you've done this before, this is pretty straightforward. If not, we're going to kind of work through it. What you do is, first, you factor your denominator. So I'm left with 1 over x plus 1 times x minus 1. Now my ultimate goal is to then rewrite this individual fraction as two fractions with each of those denominators that I get from my factors. The only problem is I just need to figure out what goes on top of those fractions to ultimately make this thing work. So for right now, I just call them a and b. Now to solve for a and b, I know these two things are equal, so I'm going to work with them. 1 over x squared minus 1 equals, here, since they're equal, I know I can actually go backwards and remultiply these things together. And I will actually point out, it does seem a little odd. You start with this, you factor it, you break it up as two fractions, and then we're actually going to FOIL it back together again to get back where we started, to figure out what a and b are. So it's kind of a circular trick, but it works well. If I FOIL here, the common denominator is clearly x plus 1 times x minus 1, which is x squared minus 1. But then I would multiply this over here and that over there. So I would get a times x minus 1 plus b times x plus 1. But the key point here is I know these two things are equal. Their denominators are equal, clearly, and their numerators have to be equal. So now I can just set the numerators equal. 1 equals ax minus a plus bx plus b. And I'll actually point out at this point, there are different ways to algebraically find a and b. And I'll do it one way. Your book might occasionally do it a different way if you watch videos online or whatever, or Google this, partial fraction decomposition. There's lots of different ways to do this. There is kind of probably, from my perspective, the easiest way to do it, but it is by no means the only way to do it. So just be aware of that. And the easiest way, I think, to do it is to actually not do that at all. And just rewrite this the way it started. A times x minus 1 plus b times x plus 1. Now, this has to be true for all x's. So what I want to do is pick x's that will make this easily solvable. Case in point, I'm going to let x equal 1. If I do, that goes away. Then I just have an equation in B. 1 equals A times 1 minus 1, which is 0, so that's just 0, plus B times 1 plus 1, which is 2. Divide the 2, and B is equal to a half. Now I can do the same thing. Again, let x equal -1. Now this term goes away, and I get 1 equals A, -1 minus 1 is -2, plus 0, which means this doesn't matter. Solve for A, divide the -2, A equals -1/2. And again, that is one way to do it. Look at all your factors, figure out the x that will make the factor 0, plug that in, and then solve for the other variables. There are other algebraic tricks we can use, and in some cases we'll actually have to use them, but this is probably the easiest and most direct. But what it means is, this is actually A, which is -1/2 over x plus 1, plus B, which is 1/2 over x minus 1. And I am aware that I can bring the 2 to the bottom. I'm actually deliberately writing it this way for what we'll see in a minute. But if you want to bring the 2 to the bottom and all of that, you can. Because now, this is equal to that, so now I'm going to rewrite my integral. That's equal to the integral of -1/2 times 1 over x plus 1 plus 1/2 times 1 over x minus 1 dx. Now when I integrate, these constants are just going to float through the problem, which is why I kind of kept them separate. And I don't need to worry about them. I just need to integrate this and this. But this, you should remember from Calc 1, that's just the, if you anti-differentiate that, you get the ln. And now immediately, this becomes -1/2 times ln, remember the absolute value of x plus 1, plus 1/2 times the ln of x minus 1, plus c. And I get that nice, simple integral to solve using my understanding of ln's and their derivatives. And I'll point out a couple of things. One that I mentioned in the last video with trigonometric substitution, we haven't integrated anything yet and gotten this big, long expression with multiple ln's in it, which makes sense. This is a new type of integral with a new trick, so it should result in different functions that we haven't seen before. The other thing I will point out, there are different ways to write this. You all kind of know your rules for ln's. You can write it like this, which I'm fine with. If you wanted to bring those coefficients in as powers, then combine the ln's. Sum of ln's is product of log. Sum of logs is log of product, and write this as one big log. You could do that if you wanted to. I'm fine. I'm completely fine with this, where you can kind of see each term separated out. Be aware there's different ways to write this. I'm not really all that concerned with that. I would point out, again, similar to what I said with the trig sub last time, the integration part's actually really easy, ln's. It's just all the algebra you have to do to get there that can be time consuming, and there will occasionally be times where these integrals will still not be the nicest integrals to work with, but doing the partial fraction decomposition will at least simplify it a little. But most of this then boils down to understanding partial fraction decomposition and being able to do it. So, suppose we have, let's see, the other one I wanted to do, which was right here, the integral of 5x squared plus 20x plus 6 over x cubed plus 2x squared plus x dx. And again, I point out that thing looks really awful, and beyond maybe getting lucky and doing a u substitution, where this is my u and that turns out to be my du, there's really no way I can solve this with any tricks that we know. So the partial fraction decomposition is the way to go. So then I just go through my trick. I start off 5x squared plus 20x plus 6 over, if I factor the bottom, there's a common x. Factor that out and you're left with x squared plus 2x plus 1. But then this is a perfect square, so I'm actually going to factor it again as x plus 1, x plus 1. Or x plus 1 squared if we want to write it that way. Multiple ways to write this. But now, if you remember your rules for partial fraction decomposition, we have to do this one slightly different. I have an x, so I put an x there. I have an x plus 1 squared, but I can't actually put in the x plus 1 squared because a possible partial fraction decomposition could include a linear x plus 1. Which means I have to account for that even though I don't explicitly see it here. And then I put the x plus 1 squared here. The idea being, if you have linear factors that are repeated, raised to a power, you have to account for all of those powers. That's squared, so I have the linear power and the quadratic power. And yes, what that means is as these factorizations get bigger and bigger, this gets much longer. So just be aware of that. It's maybe one of the downsides of partial fraction decomposition, unless you like it, which I do. But now on top, I do the same thing. A, B, and C. Now we set it up the same as before. On the left, I'm going to get 5x squared plus 20x plus 6. On the right, I know I'm just going to find the common denominator, and it's clearly right here, x times x plus 1 squared. So now I just see, I have an x here, so I have to multiply by x plus 1 squared there. I have an x plus 1 here, so I have to multiply by x and x plus 1. I have an x plus 1 squared here, so I multiply by x. So now if I write it out long form, I get a times x plus 1 squared plus b times x plus 1 plus c times x. Now I just run through different x values to get the values of my a, b, and c in this case. Start with, we'll go with -1, because that will make that 0 and that 0, so then I'll get c. So let x equal -1. Then I get 5 times -1 squared is 5. 20 times -1 is -20. Plus 6 equals a, -1 plus 1 is 0, so that goes away. -1 plus 1 is 0, so that goes away. C times -1 is -c. So now I can solve that. 5 and 6 is 11, minus 20 is -9. Divide the negative, c equals 9. And I'll put a box around it because I tend to lose these things amidst all the algebra. Next, make x 0, then these will go away. So let x equal 0. Then I get 0 plus 0 plus 6 equals a. 0 plus 1 is 1 squared, which is just 1, so that's just a. Plus, if that's 0, the whole thing is 0. If that's 0, the whole thing is 0. And I'm just left with a. So I get a equals 6. Nice and simple. But now there's a problem. If I want to find, well, I have C and A, I need B. But I've already used -1, which made those 0. I've already used 0, which makes those 0. There's no other zeros for that factorization there. So what do? And essentially the idea is, since I know this works for every x, I picked 2 x's to use here. Just pick a third x. And you can pick any x you want. Generally speaking, the way I go is you start at 0. I've already used 0. Then I kind of cycle outwards from 0 with integers. So I did 0. Now I use +1. I haven't used that yet, so I'm good. If I needed to do it again, I'd use -1. Oh, I've already used it. Then I go back to +2. It doesn't actually matter. Pick any number you want. I just try to pick small numbers that are nice. So here, we'll let x equal positive 1. Now plug in. 5 times 1 is 5, plus 20 times 1 is 20, plus 6 equals, now I have to actually plug in the values I found. A is 6, so I get 6 times x is 1. 1 plus 1 is 2 squared, which is 4, plus b times 1, so that goes away. 1 plus 1 is 2, plus c, which is 9, times 1, so that's just 9. And while it's a little bit convoluted, I still end up with an equation just in b, so solve for it. 5 and 6 is 11 plus 20 is 31, equals 6 times 4 is 24, plus 9 is 33, plus 2b. Subtract the 33, 31 minus 33 is negative 2, equals 2b. Divide the 2, b is negative 1. Which then means, up here, I'll just erase all of this. A is 6, B is negative 1, C is 9. Now I go back over here, and I'm going to have to erase all this just so we have room. But I guess that's a good thing about a video, you people can just pause it. And I rewrite this as the integral of 6 over x plus negative 1, so minus 1 over x plus 1 plus 9 over x plus 1 squared dx. Integrating term by term, the 6 is a constant, then I'm left with the antiderivative of 1 over x, which is just ln of x, minus 1 over x plus 1, that's the ln of x plus 1, absolute value. Here, the 9 floats through. I'm left here with the integral of dx over x plus 1 squared. I already pulled the 9 out. Different ways to do this, but in this case, this is just the integral of x plus 1 to the negative 2 dx into a u substitution. U is equal to x plus 1, so du is dx. That becomes the integral of u to the negative 2 du. Integrate that, raise the power by 1. Negative 2 plus 1 is u to the negative 1. Divide by negative 1, and I get negative 1 over u, which is negative 1 over x plus 1. And I do point out, because this becomes more and more likely as we learn more and more of these tricks. You learn a trick, partial fraction decomposition. You do all the algebra to get your partial fraction decomposition, which then gives you this integral with multiple terms that you can solve out term by term. But then one of the terms requires you to go back to one of your other tricks, in this case u substitution, to then ultimately get the solution. This will become 9 times negative, so that'll be negative 9 over x plus 1. All of that plus c. And essentially what that means is you're not allowed to forget any of the tricks you know, because on a lot of problems, you use one trick, which then, once that simplifies the problem, then requires you to use another trick, and then maybe even a third trick. Ultimately on your exam, just so we are clear, the way it's going to work is, I'm going to give you a bunch of integrals, and you're going to have to solve all of them. I don't care about the trick that you use. You'll have a bunch of tricks. You just need to be able to solve the integral. Some of them can be solved in more ways than one. Some of them you essentially have to follow a pretty straight line approach to get from A to B. But ultimately, it's up to you to solve them. You do just need to be able to solve them algebraically. You can't throw them into your calculator and get the answer that way. Which means you need to be able to show all of your work so I can see what you did. And then the solution you get has to actually make sense in the context of the problem. so it doesn't look like you just scribbled a bunch of math and then had Maple or something do it for you. So be aware, this is kind of the goal. Be able to integrate anything that I give you using all the tricks that we know. Okay. These videos tend to get rather long because setting up and solving these problems can be rather cumbersome. But let's see. These are brand new markers, so they're nice and bright. That also means they don't erase very well. But let's see, where's the one I wanted to solve now? We'll do this one. The integral of 2x cubed minus 4x minus 8 all over x squared minus x squared plus 4. dx. We understand this is really messed up looking, so we're probably going to go with partial fraction decomposition. So I set it up. 2x cubed minus 4x minus 8, and I have to factor the bottom. If I factor an x out there, I get x, and then I'm left with x minus 1. Here, that is irreducible. It's a sum of squares, not a difference of squares. So it's reducible in the complex, but not in the reals. You all know that. So that can't be reduced. So I set up my decomposition, a over x plus b over x minus 1. But here we have a problem. That denominator is x squared plus 4. And that's different than the other ones. And understand the difference from the last one we did, where we had, I think, x minus 1 squared. This is a linear term, that is a linear factor that is squared. This is an irreducible quadratic factor. If I have a linear factor that is squared, then I just account for x minus 1 and x minus 1 squared. If it was cubed, I would throw in an x minus 1 cubed, as long as the factor is linear, a, b, c, like we did on the last problem. However, this, if it's an irreducible quadratic term, on the top, I already have a b, I have to put cx plus d. The idea is, this is linear, so the numerator is a constant. It's degree 0. Linear, degree 0. This is degree 2, quadratic. So above it, I have to account for every possible thing on top, so I lower the degree by 1. Quadratic, I write a linear term. If you're kind of following the logic, if I had an irreducible cubic term, then I would have a quadratic term on top. We're not going to do any of those. But now I just have to find all of these. So first, my common denominator is just going to multiply these together. So a will be multiplied by x minus 1 and x squared plus 4. B will be multiplied by x and x squared plus 4. Cx plus d will be multiplied by x and x minus 1. Which means I'm going to leave a lot more room. And I get 2x cubed minus 4x minus 8 equals a times x minus 1 times x squared plus 4 plus b times x squared plus 4 plus cx plus d times x minus 1. And now I have to find all 4 of these. So I do the same thing. Let's see, I'm going to pick my x. I'm going to start with x equal to 1, because I know that'll go away and that'll go away. So I should be able to get b. So switch colors so we can keep everything straight. Let x equal 1. I get 2 minus 4 minus 8 equals, if x is 1, this whole thing goes away. B times 1 is b. 1 squared is 1 plus 4, 5. So that's 5b. Here, x is 1. That goes away. So I just have this. Minus 4 minus 8 is negative 12. 2 minus 12 is negative 10. So b equals negative 10 over 5, which is negative 2. Now I pick another x. If x is 0, these will go away. So let x equal 0. And I get 0 minus 8 equals a 0 minus 1 is negative 1. 0 squared is 0 plus 4. B times 0 is 0. All of this times 0 is 0, and that goes away. And I get negative 8 equals negative 4a. A equals negative 8 over negative 4, which is positive 2. But now we have a problem. I used x equal to 0 to make that one 0. I used x equals 1, 0 to make that 0. This is irreducible. There's no x's that make that 0, which means I'm kind of stuck. But I can do what I did before, pick an x, plug it in, and solve. But in this case, I have two variables to solve for, c and d, which means I need to pick two constants to solve for. I need to pick two x's, plug both of them in, get a system of equations, solve the system, and then get my c and d. This is a very algebra-intensive trick. So, right over here, let's see. X is 0, x is 1, so I'll let x equal negative 1. If I do that, negative 1 cubed is negative 1 times 2 is negative 2. Negative 4 times negative 1 is positive 4. Minus 8 equals, a is 2. Minus 1 is negative 2. Negative 1 squared is 1 plus 4, 5. Plus, b is negative 2, so we'll just do minus 2, times x, which is negative 1. Negative 1 squared is 1 plus 4, 5. Plus, make sure to keep it in parentheses, c times negative 1 is negative c plus d, which is d minus c. Negative 1 times x, which is negative 1, times negative 1 minus 1. I'm out of room here, but that's a negative 2. Give you a moment to write all that down. Now simplify. Negative 2 minus 8 is negative 10. Negative 10 plus 4 is negative 6. 2 times negative 2 is negative 4 times 5 is negative 20. Negative 2 times negative 1 is 2 times 5, which is 10. Negative 1 times negative 2 is positive 2 d minus c. So now simplify this. Let's see. Negative 20 plus 10 is negative 10. Add the 10 over, I get 10 minus 6, which is 4, equals 2 d minus c. Divide the 2. 2 is equal to d minus c. That's one equation. Now I need to pick another another x, and do another equation. So maybe we'll go over here, so we have room, and I will let x equal 1, 0, negative 1, we'll go with 2. So plugging it in there. 2 cubed is 8 times 2, which is 16. Minus 4 times 2 is 8. Minus 8 equals a, which is 2, times x, which is 2, minus 1, which is 1. 2 squared is 4 plus 4, 8. Plus b, which is negative 2. Times x, which is 2. 2 squared is 4 plus 4, 8. Plus x is 2, so that becomes 2c plus d. X is 2. 2 minus 1 is 1. 16 minus 8 is 0. 8 times 2 is 16. 8 times 2 is 16 times negative 2 is negative 32. 2 times 1 is 2. Distribute it in. You get 4c plus 2d. 16 minus 32 is negative 32. Add it over. You get 16 minus 32 is negative 16. Add it over. You get 16 equals 4c plus 2d. Divide everything by 2 to make the number smaller. You get 8 equals 2c plus d. Now I have a system of equations which I can solve. And again, we're ultimately going to have to erase all this because the amount of room it takes. So I'll just throw it over there. So I get, let's see, this one, 8 equals 2c plus d. That one, rearrange it so they're in the same order. 2 is equal to negative c plus d. Now solve that. Just combine, sorry, I had negative c plus d. Okay, good. I'm going to multiply the bottom equation by negative 1. So 8 equals 2c plus d. If I multiply this by negative 1, I get negative 2 equals c minus d. Now combine them. 8 minus 2 is 6. 2c plus 3 is cc. 3c, d minus d is 0. So 6 is 3c. So c is equal to 2. Now, just plug that into that one. 8 equals 2 times c, which is 2 plus d. 2 times 2 is 4. Subtract the 4. 4 equals d. And finally, a, b, c, d. And yes, this is cumbersome, and that's just kind of how it works for this. So if I go up here, I get a, which is 2, b, which is negative 2, then I get c, which is 2x plus d, which is 4. Now I'm checking my notes to see if I actually got the exact same thing for this, and I did. Good. Now I have to erase all this so we can actually write out my integral. So this becomes the integral of 2 over x minus 2 over x minus 1 plus 2x plus 4 over x squared plus 4 dx. Now I have to solve that. And I'll just kind of point out, this video is really long at this point. Antiderivative of 2 over x is 2 ln absolute value x. This, using a u sub, pretty straightforward, it's minus 2 ln of x minus 1. Plus the integral of 2x plus 4 over x squared plus 4 dx. We got the first one done. We got the second one done. Those are straightforward ln's. How do we solve that? And the problem is, well, u substitution comes to mind, but if I do a u substitution, I'll end up getting a 2x, which is there, but then I have this 4 floating around, which doesn't work for my u substitutions, so that's out, so what do I do? And in this case, like I said, this is where it's up to you to come up with more integration tricks. And in this case, we're just going to focus on this right now. If I have the integral of 2x plus 4 over x squared plus 4 dx, the actual trick, since I know u substitution will work, is to rewrite this as two integrals. 2x over x squared plus 4 dx plus the integral of 4 over x squared plus 4 dx. Now I solve each of these individually. Here, I do my u sub. U is x squared plus 4. Du is 2x dx. So this integral becomes the integral of 2x dx is du over u, which is ln u, which for us becomes ln of u, which is x squared plus 4. So over here, I just get an ln of x squared plus 4. Now I just need to solve this one. And this one, I would point out, I'm going to leave the algebra up to you simply because this one problem has taken so long already. And there's actually two ways to go here based off of Calc 1 and what you remember, or even if you don't remember Calc 1. If you remember Calc 1, they give you a chart that you can use to memorize some of these. This is actually the integral, or if you integrate this, you get arctan. You have to manipulate it a little bit. It ends up being, in this case, when you plug into the formula, arctan of x over 2, because of the 4 right there. If you remember that chart, then you can just pull this out of the air and be fine with it. You should have done that in Calc 1. Alternatively, you can rewrite this, if you pull the 4 out, as the integral of dx over x squared plus 4. That almost looks like a Pythagorean theorem, which means you can do a trigonometric substitution on this and solve it that way. I'm going to kind of leave it up to you. Those of you who remember those formulas from Calc 1, you can just pull this out of the air. Those of you who wanted to try a trig sub, you can do that too. But again, the idea being, I have this complex thing, I do the factorization, that the partial fraction decomposition, I do all the algebra for that, I get a system of equations which I then solve, I then plug in here and break it up, then I integrate each of those individually, but unfortunately one of those integrals becomes a challenge to work with, so then I have to break that up into multiple integrals, apply a u sub to one of them, here either a trigonometric substitution or randomly remembering that formula from when I was in Calc 1, and ultimately all of these things can be worked together into one actual problem. So, if you actually want to see the full solution written out, we already have it here. 2 ln absolute value x minus 2 ln absolute value x minus 1 plus ln absolute value of x plus 4. Plus, like I said here, if you factor the 4 out, you're left with arctan, or write it this way, tan inverse of x over 2, all plus c. And, this is actually a 2 if you work with all the algebra. As I didn't like the algebra out here. If you actually go through all the algebra, that becomes a 2. Because it would be a 1/2 floating around once you do that, which will cancel the 4. But again, the point being, now we can solve problems and get these incredibly long, messed up answers. If you would like to see more of these worked out, like I said, this video is already nearly 40 minutes long. I will gladly make another video going through more of them. Just let me know. And like I said, I'll also copy over those videos from my pre-calc class working on partial fraction decomposition, so you can see that worked out. There is one last thing, assuming you're all still watching this, that I wanted to mention, and we're not going to solve this one out, but just to kind of give you an idea. Suppose I have the integral of x cubed plus 3x squared plus 5 dx all over x squared plus 7x minus 1. We're not going to solve this. This wouldn't solve nicely. But the idea is, supposing you had that, what would you do? In this case, partial fraction decomposition only works if the degree on top is less than the degree on the bottom. That's not true here. So we can't use partial fraction decomposition. We also can't use, well, any other trick that I know. So what do I do? And in this case, much like using the partial fraction trick, I actually have to use another trick from way back in pre-calc. If the degree on top is greater than the degree on the bottom, do polynomial long division. I'm not going to do it here, but we all understand if I do the long division, I'll end up with an expression, a polynomial, which I can integrate term by term, plus a remainder. The remainder term will have the degree on top less than the degree on the bottom. then I can either integrate that directly, maybe I'll get lucky and there's a U sub I can do, or arc trig function. If not, I can do partial fraction decomposition on the remainder. And again, the idea here, a lot of the tricks that we know are algebraic in nature. That's why you have to do pre-calc before you do this stuff. And if you learn those algebraic tricks, you can apply them over and over to make complex problems easier. Partial fraction decomposition solves some integrals for us. Polynomial long division. Trigonometric integrals, we use the power reducing identities a lot. So all of those things from pre-calc, you're allowed to use all of them to make this problem solving easier. Like I said, I'm going to leave this here now, and because the video is long enough. If you want more examples worked out of either this partial fraction decomposition or trigonometric substitution, just let me know and I'll gladly make a video doing more of them.